Today we're going to start taking a look at functions. When I hand out the homework, remind me as well, there is one correction to the homework that we're going to mark out problems. It's always a good correction to make, right? Yeah. Okay, to start with, you're going to define what a function is. A function is a relationship between the input, called the domain, and the output, called the range, such that each input has only one output. And I just want to give you some sort of word picture examples, real life kind of stuff that fit this description. I'll do one, and then one that doesn't fit this description. So let's say that my input, that is my domain, is all people. I mean all. And the output is that person's biological mother. This is an example of a function. You select a person, and they have one and only one biological mother. Guaranteed, right? There's no other way that that works. But if I flip it, I would have a non-example. So, and it's not exactly flipped because it's got to make sense, but I'm going to take my input is all mothers, okay? So we're going to just take mothers as the input. And then the output would be that mother's biological child. Why is this not a function? Yeah, because that mother, whoever you selected, could have more than one biological child, right? So each input does not have exactly only one output in that scenario. So this would be not a function. Okay? And we're going to do a couple more examples in terms of maybe things that look a little bit more like math-related ideas. But this is the relationship that this is talking about. All right, so here is an example that's in sort of a table format. You're going to have lots of different formats, and I'm just going to show you a couple of examples. The domain is all the values that are on the left-hand side, -3, -9, 9, 7, -7, and 9. And the range happens to be letters in this case, GG, DD, GG. And what we want to know is if each input, each domain value, has only one output. Now, the fact that it's written in a table and it's sort of organized the way that it is might lead you to believe that this is a true statement. Each input has only one output. This is not true for this one. Does anyone see where the problem is? It's not because the range repeats, but that's a good idea, and that's exactly why I used the range repeating, because I wanted to show you it didn't matter. Did you have an idea? Okay, right here are two inputs that happen to match. They're on separate lines of my table, but the inputs are the same, right? The inputs are both 9s. And the output, or the range value, for one of them is D and for one of them is G. So if they both said D, even if they were repeated like this, they were both the same output or output or range value, it'd be fine. But they don't happen to be that way. So this one's not a function. But it isn't because, I need to not use red. It isn't because the range values happen to repeat, that would actually be fine. It's because there are two matching domain values whose range values don't match. So take a look at the second example. The second example is some ordered pairs. It's letters still, but that's okay. What I want to know is if each input has only one output. So what we'll do is we'll go through one at a time and see if we have any inputs that repeat. Here's a Y. Is there any other input that's a Y? No, right? The other inputs are all different, so that doesn't, so Y is good. Y has one output, its output is T. Input Y, output T, right, in the ordered pair location. The second one's a W. Are there any other inputs that are W? Nope. So input W, output Y. Okay? Each input is unique so far. Next input is K, or domain value K. Are there any other K domain values? Nope. So there's a unique input K, a unique output that goes with that K is S. And then the last one is F. And we've already run out of options at this point, so it has a unique output as well. Now, it is true that I've got a couple of duplicating output values. That's not a problem. Does not matter if my outputs duplicate, okay? What matters is if the inputs are duplicating, like it was in the table, that their outputs match. And I don't even have any inputs that duplicate on this one, so I'm fine. So this one would be a function. So these two issues are okay. This one would be a function. Now, as we move into more of a graphing perspective, there is an additional fact about graphs that we can use to help us to decide if it meets the criteria for a function. So I'm going to show you that criterion, and then I'm going to tell you why it actually makes sense, okay? So here's the criterion. It's called the vertical line test. You've probably seen it mentioned before. And it says something like this. When a relation is drawn graphically, and any vertical line intersects the graph in more than one point, then the relation is not a function. And I'd like to draw just an example of this happening so you can see why it would fail that definition from the previous screen. If my graph looked something like this, could I draw a vertical line that would cross the graph twice? Could I do that? Yeah, I could draw lots of them actually on this one, right? So we'll draw one in. This right here, the fact that I can draw this line crossing the graph twice means that it's not a function, according to the vertical line test. But let me go back with this test to talk about why, from the definition, it doesn't work. This location where it's hitting right here, this vertical line has an x value, right? Let's just give it a name. Let's say that x value is 4. Well, that same x value is the x value right up here, right? Also a 4. And it's the same x value down here, right? These all have the same x value. They're all 4. Now, the parts that are on my curve, the top and the bottom of this sort of sideways parabola-looking shape, the top and the bottom, both of those have different output values, right? They're not the same. So I have the same input, x, the same domain value, right? But there are different output values. And that's exactly what it means for something to be, not a function. I can't have the same input and different outputs, not if it's a function. Okay, so that's why the vertical line test works, is because it isolates a specific domain or x value and it checks to see whether it crosses twice, i.e. has two different y values. Okay, so we're going to do 3 examples of those. All graphical standpoints, of course. I don't have any of them drawn in yet. It's really difficult to get those things to sketch the way I want when I'm on the computer screen. So this is my first graph. It's just a bunch of dots. And this is my second one. Okay, so the cool thing about the vertical line test is that it's very visual. And so I know some of you are probably very visual learners. I'm really visual. If I can see it, I can usually remember things. If I just hear things, I'm probably going to forget it. So if I can look at this graph and I can test the idea of sort of dropping in these vertical lines, I can use that to decide if I have a function. So if I were to drop in vertical lines on the first graph, many of my vertical lines don't hit anything, right? And that's totally cool. There's nothing wrong with that. I don't need all my vertical lines to hit something. Some of my vertical lines hit the graph in one place, right? It hits one dot. So all those things are fine. But the question is there any vertical line that could be drawn where it would cross the graph twice? And there is, right? What vertical line would cross the graph twice? Yeah, the one that crosses over here at -3, right? This actually has a name. This line would be x equal -3. If I drew in a line at -3, I would hit 2 points on my graph. I mean, it's not a very exciting graph, it's just a bunch of points. But it still fails, right? There are 2 inputs of -3 with different outputs or different y values. So, if that happens, this would be not a function. What if I tried that same thing on the next graph, on example 4? Draw me some vertical lines in there. Do you have any vertical line that will cross the graph twice? Not a vertical line, right? And we're only talking vertical, so don't go changing it to a different type of line. Vertical lines will always cross this graph only one time, right? So, is this a function? Yes, it is. This one would be a function. Let's try one more. Go with that. Is this graph a function? Not a function. Why not? What's the problem? Yeah, many lines, right? Not all, but many of them, and all I need is one. So there's an example of one right there. Draw one in to justify my claim, where I'm crossing the graph twice. So it's not a function. Now when we have a function, there are better than, that was a terrible way of saying it. Let me try that again. There are some ways that are better than others to write down an equation. And when we have a function, we have a better way to write it than we have been writing them. So many times we have equations and they're written y equals something or other, right? Okay, so when we have functions, we have another way of writing them that are more helpful. So y equals f of x. So this is red. F of x, okay? It is not multiplication. This is not f times x. I know parentheses sometimes mean multiplication. These don't. It means that x is our domain and y is our range. And it means that we're dealing with a function. In particular, it passes that vertical line test. Every input has only one output. So for example, if you had this notation written down here, this means x is 7, y is 5. That's what that notation means. The number inside is x, the number it equals is y. So we're going to do an example where we're going to be given some functions and we're going to be asked to evaluate them. This isn't anything new. We've evaluated things a lot, okay? But the notation we haven't used. That's the part about this that makes it a little different. Am I good to go to the next slide? All right, so don't get too far ahead. I've got several examples on the slide. Just write down the question first and part A. So we have two equations here. One of them says f of x equals negative 2x squared minus 3. And the second one says g of x equals 5x minus 5. And the first one we're trying to find is f of 6. This does not mean multiply by 6. So I'd like for you on this one at least to jot yourself a note that says what this is doing. This is saying use f of x equation with x equals 6. That's literally what it's saying. It's saying come up to this equation, and everywhere I have an x in it, substitute in 6. So it would look like that. Replace x with 6. And then you're literally going to compute. Grab a calculator if you want. Grab a sheet of paper. Mental math, whatever it takes. When I'm looking at this, negative 2, 6 squared minus 3, what is the first part of that I would do? The 6 squared. What is 6 squared? 36. And then I would have negative 2 times 36, which is what? Negative 72. And what's negative 72 minus 3? Negative 75. Show steps, don't show steps, I don't care, just as long as you're being super careful on the calculations, we'll all be good to go. Order of operations matters, of course. So if this idea is written down again on part B, what is part B telling me to do? To use g of x equation with what? Right, with x equals negative 5. So that's the other equation at the top that I've highlighted or underlined in pink. So I would have 5, and I would plug in negative 5 for x, and then minus 5 at the end of the equation. So I have 5 times negative 5 at the beginning, which would be negative 25. And what is negative 25 minus 5? Negative 30. Is everybody okay with that? Okay, the next two are a little bit different. They're not numbers, right? I mean, it says 3x inside of the parentheses on the next one. So if we're thinking in the same way, what do you think that it's telling you to do? Replace x with 3x. In which equation, Sarah? In f. So this is literally saying the same thing. Use the f of x equation. With the x replaced by, I'll use words because it looks funny, replaced by 3x. So I'm going to have negative 2. It was x inside. Now it's 3x squared. And then minus 3. Now my answer in the end is not going to be a number, right? It's going to be an equation with an x in it. That's all right. What happens when I square 3x? Ooh, I get 9x squared. Good job remembering to square the 3 as well. And then what is negative 2 times 9x squared? Good, negative 18x squared. And then I just have the minus 3 on the end. How about you give part D a try? It's the same idea. Make sure you're using the right equation, you're replacing the right pieces, and then confirm with a neighbor and see if you have the same answer at the end. Okay, so most of you check with somebody. If you haven't yet done so, double check with somebody nearby you. Make sure that theirs looks like yours or yours looks like theirs. Okay? Okay, so you should have taken the g of x equation, which is 5 times. It was originally x, now it's x plus 3 minus 5. Did you distribute the 5? Fabulous. I'll write mine down here since I have space. 5x plus 15 minus 5, so we should have ended up with 5x plus 10. Is that look good? Great. All right, this is different. So jot this down. Again, don't go beyond part A. Just write down the pieces in front and then part A. This is called a piecewise function. Okay, the questions it's asking are no different than before, but the function is defined differently. It's defined on pieces. So if you can kind of imagine what a graph would look like, I'm not going to draw the graph of this, but I can kind of think about what I have is I have this graph, and it's split up into 3 sections. They're not equal sections, by the way. It's just 3 of them. One section is from -1 to the left. So it's something happening over here. One section is between -1 and +2. It's sort of the in-between section, and it's doing something else in here. And then there's a third section of the graph that's bigger than 2. And that's defined here at the end. The first piece of the graph is for before -1, the second piece is between -1 and 2, and the third piece is after 2. Okay, different equations for different parts of the graph. So far, so good. So here's how this plays out here. When it asks you to find, in this case, g of -3, you have to decide which piece of the graph it's on. Is it on the first piece at the top, the second piece that's written in the middle, or the third piece that's written on the bottom? So which piece of the graph am I on if I am at an x value, right? That's the interior here. This says x is equal to -3. Where am I? I'm in the first one. Because over here it says these are the x values that are less than -1. -3 is less than -1, right? And then this tells me right here what the y value's output is. It's very easy. It's -1, right? So my output here, I don't even have to evaluate anything on this one, is just -1. How about the second one? Part B. This says my x value is -1. What part of the graph am I on, first, second, or third part, if my x value is -1? Somebody say it loud for me. Which part do you think I'm on? First one? Because of this piece? Okay, so let's be careful. Both that piece and this piece have the x -1 parts attached to it, right? Which one fits when actually x is equal to -1? The second one. Yeah, that's why I wanted to throw that in there, because I want to make sure we're reading the equations or the inequalities carefully. The second piece says x is equal to -1. So in our case, we're on this piece if we're at x equal to -1. Which means that I'm going to use this equation to plug -1 into. So I would have negative, and then I have -1 minus 1 squared plus 2. So where do I start when I'm simplifying that expression? Order of operations. Y'all know this. Where do I start? Inside the parentheses. So what will the inside of the parentheses become? What? Yeah, -2, actually, right? -2. So I have negative, and then I have -2 squared plus 2. I'll square next. So what's -2 squared? 4. So this negative at the beginning is still there. And then I have 4, and then plus 2, which gives me what? Yeah, -2. All right, part C. This says that the x value is 1. Which line am I on if x is equal to 1? It's still the second one. How come, Megan?
Because x is greater than or equal to -1 and less than or equal to -2, so that falls in the middle.
Yeah. These are values that are between -1 and +2. Well, that's where the number 1 is.
So we're only like comparing it to the right side.
The right side tells you when you use which part of the equation. And again, I did that on purpose because I don't want you to be like, oh, like the first one's always going to be the first line, and the second one's going to be the second line, and the third one's going to be the third line. It's just not always like that. You have to decide which piece you're going to plug it into. And it fits in here, right? My x value is the number 1. And the number 1 would be between -1 and 2. So I would be in the second line of our piece. piecewise equation, just like I was before. That actually solves really nicely. So if I plug that in, then I've got negative, and I've got 1 minus 1 squared plus 2. Well, it's 1 minus 1. 0. So this whole piece is 0, right? Which means that this will just become the number 2. So you first have to decide which piece of the equation you're on, and then you follow the instructions for that piece. All right, the next thing that we're going to look at, we've seen before, we just haven't seen it used with this language. We have a rational function here. It says f of x equals x plus 6 over x squared plus 7x plus 6. And it wants us to find the values that are not in the domain. We had this same question in the last unit that we did, and we called it restricted values. What values are restricted? It's the same question. We just have the word domain that we're able to use now, where we didn't have that defined before. All this is asking is, what can x not be? And in particular, on this one, since I'm looking at an equation with a denominator, you do know that there is something a denominator cannot be. What can the denominator not be? 0. Now, that doesn't mean x cannot be 0. It means the whole denominator cannot be 0. Right? We know that the denominator cannot equal 0. So we're going to figure out what values for x would in fact make the denominator equal to 0. So we have x squared plus 7x plus 6, and it's supposed to be not equal to 0. So this one factors. How will x squared plus 7x plus 6 factor? X plus plus, 1 and 6, that'll do it. And then we set each of these to be not equal to 0. So what in fact can x not equal? Yeah, it cannot equal negative 1, and x cannot equal negative 6. And those are in fact the values that are not in the domain, negative 1 and negative 6. Because it would give me a 0 on the denominator. Now, it's worth noting that the numerator has nothing to do with this problem, right? So no matter what was on top, the answer would remain the same for this question. Now, the next question is going to ask the same thing, but in a slightly different way. Instead of saying what values are not in the domain, it actually asks you to find the domain. So instead of saying what can you not have, it asks you what can you have. You with me? It's the same question, it's just posed in the opposite way. So on this one, we have a radical. What do you know about square roots with real numbers? We've done complex numbers too, but what do you know about square roots with real numbers? What can you not have? Negatives underneath radicals, right? When we had negatives underneath radicals, we were getting imaginary units out of it, right? We're working in the real number system, so we don't have negatives underneath the radical, which means the part that's under the radical has to be what? What was it? We don't want a square. We're asking for what kind of values can we have? Huh? Okay, you're giving me already the solved version. Okay, so you just told me that we can't have negatives. So what can we have? Positives, thank you. In particular, we could have positives, or even we could have 0, right? What's the square root of 0? 0, right? Square root of 0 is 0. So I need whatever I have underneath my radical to be positive or 0. So what would this solve to being? This is where Lauren was telling me. 6, right? Yeah, I would add the 6 to both sides, so this is greater than or equal to 6. Now, there's another part of the directions we'll get to next time, which says as an interval. But let's answer 10 real quick. X can't be what? It can't be 8. Everybody good with that on number 10? It's a simpler version than what we just did before where we had to factor. X cannot be 8 on number 10. So we'll pick back up on Wednesday with this lesson where I can show you what it means about this interval business. And then I have just a couple more quick examples after that. So we won't finish this one today. We'll finish it on Wednesday, which means this is due on Thursday. And I'll go ahead and save it since you don't need it anyway because you're not going to be doing it. So I'll just hang on to them.